Hello everyone. In this lecture we will talk about the properties of the DFT, the discrete Fourier transform. But before we do so, we need to realize the fact that the DFT equations we have seen so far, the two equations for computing the DFT and the inverse DFT, these equations treats the endpoint signal x of n and its DFT coefficient x of k as primary periods of periodic sequences x tilde of n and x tilde of k. In other words, the mathematical equations deal with x of n as one period of a periodic signal and deals with x of k as one period of a periodic signal. How is that? If you remember, we have previously talked about the fact that having a discrete time signal results in periodicity in frequency domain, and omega becomes periodic with period 2 pi. And now, since we are having sort of sampling in frequency domain, and k now is the index of frequency, we will be having periodicity again, but now in a discrete variable called k, and it will be periodic every n capital. Because as we have seen before, n capital corresponds to 2 pi. So here we have periodicity in k domain. So x of k is periodic and it has a period of n capital. And the equations of DFT and IDFT sees x of k as one cycle of a periodic signal, x tilde of k. Same for x of n. Since we have discreteness in frequency domain right now, this discreteness or sampling in frequency domain results in periodicity in time domain. So we have x tilde of n. So again, the equations does not see x of n, which is only one cycle. It sees this periodic signal. So when we deal with x of n, the equations see a periodic signal, and we're only dealing with one cycle of this periodic signal. So let's read this statement one more time. A DFT treats the endpoint signal x of n and its DFT coefficient x of k as primary periods of periodic sequences x tilde of n and x tilde of k. Therefore, in order to apply the properties correctly in the DFT, we need to consider this fact. We need to consider that x of n is seen as one period of a periodic signal and x of k as one period of a periodic signal. And we need to apply the property, be it shifting in time domain or shifting in frequency domain or mirroring in time domain or mirroring in frequency domain or whatever property is on the periodic signal x tilde of n and x tilde of k. So, in order to visualize this, we need some tools that help us to deal with this periodicity mathematically and visually. And as a matter of fact, we have three ways to deal with this periodicity. The first one is called the periodic extension. That is, starting with x of k, which is only defined from 0 up to n minus 1, we create a sequence x tilde of n, which is a periodic extension of x of n. Same for x of k and x tilde of k. The second approach is to draw x of n and x of k on a circle. And this circle, as you go one time along the circle, you will get the sequence you have. If you go another time, you get the sequence again. A third time, the same sequence again, so you get the same effect of periodicity. And the third approach is to use the modulo operation, as we're going to see in a few seconds. So, one way to visualize this inherent periodicity, the periodicity we have in x of n and x of k, is to wrap the n-point sequence around a cylinder with a circumference equal to the sequence length as seen in this figure. So as you can see over here, we have a circle, and let's assume we have n capital equal to 4, so the time goes from 0 up to n minus 1, which is 3. So here we have the sample x of 0, and here x1, x2, and x3. And the time advances in this direction, which is counterclockwise. So as we advance through the time, going through the circle, we'll have the samples x0, 1, 2, 3. If the time advances from C3 to 4, we'll be going to n equal to 0 again, and we'll be seeing the same sequence of samples again. So this circular representation accounts for the periodicity we're talking about. So the first approach to deal with this periodicity is the periodic extension, that is to repeat the samples every period capital N. The second approach is to draw a circle and put the samples on a circle, and the third approach is the modulo operation. So traveling around this circle once, starting at n equal to 0, will give us n point sequence x of n. If we keep repeatedly going around this circle, we obtain the periodic extension x tilde of n, which is basically the samples being repeated over and over from minus infinity to positive infinity as a periodic signal. Geometrically, the finite duration sequence x of n is recovered by unwarping the cylinder and laying it flat on a circular time axis. That's basically having the circle you have unwrap it to be a linear scale axis. So here we have two indices, a linear time index n and a circular time index we call r, and the relation between n and r is known as the modulo operation, which is defined as if n, which is the linear time axis, is equal to L, which is an integer, times n capital, which is the period we have, plus r. R must be an integer, positive integer going from 0 up to n minus 1. So expressing n in this form, we are simply saying that n includes this number of complete cycles. N capital represents one complete cycle. So n small is equal to L complete cycles, so L times n capital plus r, and this r will point to which part of the sequence you are in right now, but it should be less than a complete cycle. R should be larger than 0 but less than n minus 1. And looking for this value of r is called the modulo operation. It has this symbol n between these triangular sort of brackets, so we can read this part as n modulo n capital. Computing n modulo n capital will give us r, which is the remainder, how many steps we have gone through a cycle before we complete a complete cycle. So how many complete cycles we have is L capital, L small, and r over here is how many steps we have gone through one cycle. So these are the three approaches we can use to deal with this periodicity. If this is x of n, first approach is to do what's called periodic extension, to repeat this one cycle from minus infinity to positive infinity to get x tilde of n. Second approach is to write this sequence x of n on a circle. And the third approach is the modulo operation. So, as we said before, n is equal to L times n capital plus r, and computing the modulo operation, we will choose L such that r is always positive integer in the range from 0 up to n minus 1. So, for instance, if n is equal to 4, and we need to compute modulo of minus 4 with respect to 4, how we can do that? Let's move to our whiteboard over here, and here we need to find minus 4 modulo 4. So, in order to do so, we need to express this minus 4 in the form we've seen, which is L times 4, which is n, plus r. And this r must be positive and must be from 0 up to n minus 1, which is 3 in this case. So, if we choose L equal to 0, this means we have 0 plus times 4 plus r, which makes r equal to minus 4, and this value is not acceptable because r must be positive from 0 to 3. What about choosing L equal to minus 1? Minus 1 times 4 plus r, r will be 0. Now this value of r is acceptable because it's positive between 0 and 3. So, as we can see right now, minus 4 modulo 4 is basically 0. So if you go back over here, minus 4 modulo 4 is 0. What about, let's say, minus 2 modulo 4? So let's go to our whiteboard over here, and we need to compute minus 2 modulo 4. So minus 2 modulo 4. In order to do so, we need to write minus 2 as L, which is an integer, positive or negative by the way, times n capital, which is 4, plus r. So if we choose L to be minus 1 times 4 will give us minus 4 plus 2 will give us the minus 2 we have. So r here is equal to 2 and the modulo is equal to 2. So going back over here, so minus 2 modulo 4 is 2. And if you keep going, minus 1 modulo 4 is 3. 0 modulo 4 is 0. 1 modulo 4 is 1, and so on. So you can see that the modulo operation is actually periodic. As you can see over here, minus 4 modulo 4 is 0. 0 modulo 4 is 0, 4 modulo 4 is 0, 8 modulo 4 is 0. It's basically saying that 8 has 2 complete cycles of 4 plus r, which is 0. So computing the modulo operation is actually looking for this r. So as we can see, the modulo operation is periodic, so we can write down that n plus n capital modulo n is equal to modulo n. So if let's say n is 0, so 0 plus 4 modulo 4, which is 4 modulo 4, is equal to 0 modulo 4, is equal to 8 modulo 4, and so on. So the modulo operation itself is periodic, with period n capital. And this will allow us actually to express the periodic extension x tilde of n of finite length sequence x of n as follows. X tilde is the periodic extension of x of n, which is defined for all n going from minus infinity to positive infinity. It's equal to x of n modulo n. In order to understand this equation, let's move to our whiteboard over here, and let's say we have a signal x of n, which is defined from 0 up to 3. So we have n capital equal to 4, and we only have 4 samples, x of 0, x of 1, x of 2, and x of 3. The first way of dealing with the periodicity we're talking about is to have x tilde of n, the periodic extension, which is simply repeating the signal from 0 to 3, and then the next cycle from 4 to 7, next cycle from 8, and so on up to infinity, and same for negative infinity. And as you can see, x tilde of n is equal to x of n modulo n. How is that? So the equation says x tilde of n is equal to x of n modulo n. So let me ask you, what is the value at n equal to 5? So x tilde of 5 would be x of 5 modulo 4, and if you compute 5 modulo 4, it will be x of 1. So as you can see, at instant 5 actually we have x of 1, which is correct. So if I ask you what's x tilde at 15, it will be x of 15 modulo 4. Compute 15 modulo 4 and you get x of 15, x tilde of 15, and so on. So x tilde of n, the periodic extension of x of n, is equal to x of n modulo n capital. Same for x tilde of minus n, which is a mirrored or time reversed signal. X tilde of minus n is x of minus n modulo n. Same for k. X tilde of k is x of k modulo n, because again we have periodicity in the k domain with period n capital. And x tilde of minus k is x of minus k modulo n. These relations are really important. You need to understand them. We can compute the modulo operation in MATLAB using the command mod. And this periodicity we were talking about in x of n and x of k can be dealt with in 3 different ways. Either by periodic extension, by drawing x tilde of n and x tilde of k, or by drawing them on a circle, this circular representation, or using the modulo operation. So now we are ready to talk about our very first property, which is the linearity property. Assume we have a sequence x1 of n whose length is n1, that is, it's defined from n equal to 0 up to n1 minus 1, and another sequence x2 of n whose length is n2, that is, it's defined for n from 0 up to n2 minus 1. Now, assume we have a linear combination y of n equal to a1 x1 of n plus a2 x2 of n. Since x1 and x2 have different lengths, first we need to make sure they have the same length before we can add them together. In MATLAB, if you try to add two sequences of different lengths, you will get an error. So the first step, you need to make sure they have the same length by adding zeros, by zero padding. So let's assume x1 has a length 5 and x2 has a length 8. So we need to add 3 zeros at the end of x1 to do zero padding to x1 to make sure its length is 8, equal to the length of x2. Then we can combine them together. So the length of the new sequence will be the maximum of n1 and n2. So if we have sequence of length 5, sequence of length 8, with choosing the maximum of n1 and n2 will give us the new length we have. So the linear combination y of n will have a length of maximum of n1 and n2. And now we can compute the DFT of the sequence y of n, whose length now is the maximum of n1 and n2, which we call ny. So computing the endpoint DFT, where n is larger than or equal to ny, at least ny, it can be larger. If it's larger, it means we do zero padding in both sequences. Now, the DFT of the linear combination is simply a1 times the DFT of the first sequence plus a2 times the DFT of the second sequence. So, the first summation is the endpoint DFT of the sequence x1, and the second summation is the endpoint DFT of the second sequence. The first sequence is zero padded by n capital minus n1 zeros, and the second sequence is padded by n minus n2 zeros. And this way we can write y of k is equal to a1 x1 of k plus a2 x2 of k, where x1 and x2 are the endpoint DFT of x1 of n and x2 of n respectively, and n must be larger than the maximum of n1 and n2. In order to better understand this property, let's move to Octave over here, and we have defined the sequence x1 of n equal to 1, 2, 3, 4, the length of which is 4, and the sequence x2 of n, the length of which is 7. So n1 is equal to length of x1n, which is 4, and n2 is equal to the length of x2n, which is 7. So clearly they have different lengths. If I try to define a sequence y of n that's equal to x1 of n plus x2 of n, I will get an error message because they have different lengths. So I first need to zero pad the shorter sequence with number of zeros in order to make sure they have the same length. So I will define a sequence x1n zero padded, which is equal to x1n, and I need to have zeros of 1 and n2 minus n1. In this case, I will be having a sequence of length 7. And now I can define the sequence y of n as x1n zero padded plus x2n. Now they have the same length, and now MATLAB wouldn't complain about the lengths. This is the first part. We need to make sure the two sequences have the same length, and we usually do zero padding. Of course, I can do zero padding for both of them. So I can make the length of x2n, let's say 10 samples by adding 3 more zeros, but then I will need to add 6 zeros to x1n to make sure they both have the same length, which is 10 in this case. Now, if I compute the DFT x1k of the sequence x1n, x1n in its original form is only having 4 samples, so its Fourier transform, the DFT, also will have 4 samples. Computing x2 of k, it will have the same length as the original x2 of n, which is 7 samples. Now if I try to add x1k and x2k, I'll have a problem because they have different lengths. So when combining them in time domain, we needed to add zeros to do zero padding for x1 of n, and when computing the DFT, we will compute the DFT of the zero padded sequence. In other words, when computing x1k, I will not use x1n, I will use x1 zero padded, the sequence which has been zero padded and it has a length of 7. Now I will get x1k which has 7 samples, and x2k is the same as before. Now I can get yk, which is equal to x1k plus x2k. If I do inverse fast Fourier transform to this yk, I will get the summation I had before, which was yn, exactly the same. So the property here simply says that if you want to create a linear combination of two sequences, first make sure they have the same length. If not the same length, you need to do zero padding for the shorter sequence. Next, adding them linearly in time domain after zero padding implies that their DFT in k domain or frequency domain will be added together in the same linear manner, given that you compute the n point DFT, n being the new length of the sequence you have after you did zero padding. Okay, so the next property is called the circular folding property, which is basically a time reversal. So if you want to do the operation x of minus n, or time folding, this operation is not defined. Why? Because time reversal implies that the samples that was happening for n larger than 0 will be shifted to n less than 0, and the samples happening in n less than 0 will be shifted or mirrored in n larger than 0. Now, given that in DFT we only deal with sequences starting at n equal to 0 up to n minus 1, we'll be having a problem. In order to understand this, let's move to our whiteboard over here. So if we have a signal x of n, only defined from 0 up to n minus 1, and we need to do folding or time reversal. The idea is that in time reversal, usually the samples happening in the positive time will be mirrored to the negative time, and the samples happening in the negative time will be mirrored or reflected in the positive time. But in DFT, we only know the samples going from 0 up to n minus 1. The samples before that we do not know, and the samples after that we do not know. So doing the time reversal in this manner is not appropriate. So what is the correct way of doing things? You need to deal with the fact that the DFT equations see x of n as one cycle of a periodic signal. In other words, you have to do the periodic extension. You have to extend the signal, so from 0 up to n minus 1, and then you have to repeat this signal, so you have to work with x tilde instead of just x, and then you can do the mirror on this signal, x tilde of n. So if you want to perform any property, first you have to deal with the periodicity, either by getting x tilde of n or x tilde of k, the periodic extension, or by using the modulo operation, or by using a circular mapping on a circle. However, based on the inherent periodicity of the DFT, we can define this operation, the time reversal operation, in a mathematically consistent way by using the periodic extension x tilde of n. So as we can see over here, if you have a sequence x of n, and we want to perform this property, the folding or time reversal, or any other property, by the way, first we need to find x tilde of n. We have to repeat this one cycle from minus infinity to positive infinity, and then we need to perform the property, be it time shift, frequency shift, or time reversal, any property we're going to talk about later on, you have to do these steps. Find x tilde of n, perform the property on x tilde of n, the signal which is periodic, and then select the cycle going from 0 up to n minus 1. So in this case, as you can see, the sample happening at n equal to 0 remains as is, but all the other samples will be kind of reversed. So if this is x of 0, x of 1 will happen here at n minus 1. X of 2 will happen here at n minus 2, until we reach x of n minus 1 happening at n equal to 1. So the sample at 0 remains as is, and all other samples will be kind of reversed or flipped. This is the circular folding. This is the time reversal happening in DFT, happening when we take into account the periodicity in x of n. Same result will be obtained if we do it in a circle. So if we can draw x of n in a circle, x0, x1, x2, x3, up to x7. Doing the circular folding, basically we'll keep x of 0 as is, and reversing all other samples. So x of 0, x of 7, x of 6, x of 5, 4, 3, 2, 1. So doing circular folding on this circular mapping, on this circle, we simply keep x of 0 as is and reverse all the other samples, as if we are writing the sequence in a clockwise direction and reading the samples in a counterclockwise direction. So we write the samples x0, 1, 2, 3 in a clockwise direction, but you read them as usual in a counterclockwise direction. So circular folding can be performed in 3 steps. First, get x tilde of n, the periodic extension. Second, do the time reversal or any other property you want to apply. Then extract one cycle of this signal you have going from 0 up to n minus 1. This will be your time reversed signal, or the circularly folded signal. Same result can be obtained in a single step by wrapping the sequence x of n around the cylinder clockwise. So you write the samples clockwise and reading them as usual in a counterclockwise manner. This operation is known as the circular folding, can be defined mathematically as follows. So x of minus n modulo n, which is the circularly folded sequence, is equal to x of 0 for n equal to 0. So the sample at 0 remains as is. And for the other time intervals, x of n capital minus n small. And note that the time reversed sequence is also defined for the time range from 0 up to n minus 1. So the sample x of 0 remains as is, and the remaining samples are arranged in reverse order. X of 0, x of n minus 1, x of n minus 2 up to x of 1. And this is equivalent to having x of minus n modulo n. How is that? Let's go over here and see. So what is the sample value at n equal to 2? So here we have n equal to 2. It will be x of minus 2 modulo 8. If you compute minus 2 modulo 8, it will be x of 6. What is the sample value at n equal to 1, 2, 3, 4, 5, n equal to 6 over here? So it will be x of minus 6 modulo 8. If you compute minus 6 modulo 8, it will be 3. It will be x of 3. So in order to get the circularly folded samples, all you need to do is to compute x of minus n modulo n. So what is the property? So now we only learned how to do the circular folding. The property simply says that if you know a sequence x of n, and you know its endpoint DFT, which is x of k, the property says if you do circular folding in time domain, you get x of minus n modulo n. You will be doing circular folding in frequency domain. You will be getting x of minus k modulo n. So the property simply says that doing circular folding in time domain will get you circular folding in frequency domain. So let's see how this is going in MATLAB. So as you can see over here, we defined a sequence x of n equal to 1, 2, 3, 4, and we have the circularly folded sequence. The sample at 0 remains as is, the 1, and the remaining of the samples are kind of reversed, so 4, 3, 2. So if we compute the FFT of xn. Of course, FFT is an efficient way of computing the DFT transform, the discrete Fourier transform. So x of k would be 10 and minus 2 plus 2j, minus 2 and minus 2 minus 2j. If we find the FFT of xn circularly folded, the circularly folded signal, the property says if you do circular folding in time, you will be getting circular folding in frequency. So now I'm computing the fast Fourier transform, or the DFT, of the circularly folded sequence. So supposedly I will be getting this x of k but circularly folded, which is basically the first sample remains as is, and these samples would be kind of reversed in order. So let's try to do this. So as you can see, the fast Fourier transform, or the DFT, of the circularly folded sequence, the first sample is 10, remains as is, and all these samples are kind of reversed. The first sample here is minus 2 minus 2j, which is the last sample over here, and then minus 2, and then minus 2 plus 2j appears last. So the property simply says that if you do circular folding in time domain, you will get circular folding in frequency domain. And the circular folding in frequency domain is done in the same manner. X of 0 remains at k equal to 0, and for all other values of k, it will be x of n minus k, x of n capital minus k. The next property is a symmetry property. So if you have x of n and you know it's transform x capital of k, if you do a complex conjugate in time domain, x conjugate of n, this will give you in the frequency domain circular folding and conjugation. So x conjugate of n will get you x conjugate of minus k modulo n. And similarly, x conjugate of minus n modulo n will give you x conjugate of k. So in order to better understand this, let's move to MATLAB again. And here we have a sequence x of n that's equal to 1 minus j, j, 1, and minus j. If we compute the FFT of this sequence, we will get this kind of DFT. The property simply says that if we try to compute the DFT of the conjugate of xn, you will get circular folding and conjugation in the frequency domain. So the Fourier transform of the conjugate of x of n will simply be the same sequence, this sequence, but it will be conjugated and circularly folded. So let's try. So as you can see here, the first sample will remain as is, and it will be conjugated. Instead of 2 minus j, it's 2 plus j. And this sample will be moved to the very last sample over here and conjugated, so 2 plus j. And this sample will be over here conjugated, and this sample will move to be over here conjugated. So the property is actually happening in MATLAB. And this is the main advantage in this chapter. All the properties we're going to see you can verify very easily in MATLAB. So the property simply says that if you have x conjugate of n, you will get x conjugate of minus k modulo n. Conjugation in time domain will give you circular folding and conjugation in frequency domain. And the other way around, if you have conjugation in frequency domain, you will get conjugation and circular folding in time domain. What if x of n is real valued? If x of n is real valued, x conjugate of n is equal to x of n, which means x of k is equal to x conjugate of minus k modulo n. So for real valued sequences, if x of n is real valued, x of k will be equal to x conjugate of minus k modulo n. This means that they have magnitude of x of k will be equal to magnitude x of minus k modulo n, and the phase of x of k will be equal to minus the phase of x of minus k modulo n. We'll have even symmetry, sort of, in the amplitude and odd symmetry in the phase. It's actually called circular symmetry. So using these symmetry properties, we can achieve a very important task over here, which is the calculation of the DFT of two real valued sequences using only one DFT operation. And instead of paying the time and resources to compute two DFTs for the two real valued sequences, there is a way using these properties to compute the DFT of two different real valued sequences using only one DFT operation. How is that? Let's first define we have two sequences, x1 of n, x2 of n. Both are real valued, and the key word here that the sequences in time are real valued. And each have the same length, which is n point sequence, and they have DFTs x1 of k and x2 of k. Let's compute a new sequence. Let's define a new sequence x of n, which is equal to x1 of n plus j x2 of n. So we composed a new complex valued sequence, which is basically x1 of n plus j x2 of n. So the real part of x of n is x1 of n, the first sequence, and the imaginary part of x of n is x2 of n. And now we can compute the DFT of this x of n, x of k, using only one DFT operation. And now we can use the property, if you do conjugate in time domain, you will get circular folding, and conjugate in frequency domain. So x1 of n is the real part of x of n, so it can be written as 1/2 x of n plus x conjugate of n. Now using the property, so x1 of k, the DFT of the first sequence, will be 1/2 x of k plus, and the DFT of x conjugate of n is x conjugate of minus k modulo n. So we already have x of k, so you will add x of k plus x conjugate of minus k modulo n. This will give you x1 of k. Similarly, x2 of n is the imaginary part of x of n, which can be computed as 1/2j x of n minus x conjugate of n. Using the linearity property and the conjugation in time property, we will get x2 of k equal to 1/2j x of k, and the transform of x conjugate of n is x conjugate of minus k modulo n. So using only one DFT operation, which is computing the DFT of x of n, the newly composed sequence we have, we can get the DFTs of two real valued sequences, x1 of k and x2 of k. So in order to better understand this, let's move to MATLAB. Over here we have defined two sequences, x1 of n and x2 of n, and we need to compute the DFTs of these two sequences using only one DFT operation. So the first step is to define a new sequence x of n, which is equal to x1 of n plus j times x2n, a sequence whose real part is the first sequence and whose imaginary part is the second sequence. So as you can see over here, 1 plus j5, 2 plus j6, 3 plus j7, 4 plus j8, and so on. Now computing only one DFT operation, which is FFT of this sequence xn, this will be the DFT x of k. Now, in order to apply the property we have just seen, we need to find x circularly folded and conjugated, which will take this form, which is basically keeping the first sample as is, doing a conjugate, and -4 will be the very last sample. This will be -2 plus j2 over here, and here we have -4j, which will be +4j. So the property here says that if you want to find x1 of k, it's 1/2 x of k plus x conjugate of minus k modulo n, the circularly folded conjugated x of k. So in order to find x1 k, it will be simply 1/2 x of k plus xk circularly folded and conjugated. This will be the DFT of the first sequence. In order to make sure we have the right value, if we do the IFFT of x1k, this will give us the first sequence x1n, 1, 2, 3, 4. And similarly for x2, if you want to find x2 of k, it's 1/2j x of k minus xk circularly folded. And in order to make sure we have the right sequence, if we do IFFT of x2k, we will get x2n, which is 5, 6, 7, 8. So using this property, the symmetry property, we can compute the DFT of two real valued sequences using only one DFT operation. The next property we have over here is a circular shift. If you want to shift a signal x of n, again, first we need to extend it periodically to get x tilde of n, then do the shift on the periodic signal x tilde of n, and then select the samples starting at 0 up to n minus 1. So if you're shifting to the right by 2 samples, you will be getting samples shifted circularly like this. So if you take a look, the sample at 0 will be shifted at 2, and the sample at 1 at 3, and so on, and the very last 2 samples will be kind of circularly shifted to the beginning of the sequence. This is equivalent to putting them in a circle and shifting the samples on a circle. So the circular shift can be expressed mathematically using the modulo operation as follows. So it's x tilde of n minus m or x of n minus m modulo n. So the key point here, before performing any property, you have to take into account the periodicity we have, x tilde of n or the modulo operation or drawing them on a circle. So if you want to do mirroring the circular folding, so instead of having x of minus n, no, we should have x of minus n modulo n. If you want to do a shift, it's not x of n minus m. No, this is wrong. The correct expression is x of n minus m inside the modulo operation, n minus m modulo n. And the property simply says that if you do a circular shift in time domain, x of n minus m modulo n, you will get the same x of k multiplied by wn to the power km, where m is the shift we have. I will leave it to you guys to verify this property in MATLAB. Of course, if m is larger than 0, we'll be shifting x tilde to the right, or circularly we will be shifting counterclockwise. And if m is less than 0, we'll be shifting clockwise, or we'll be shifting x tilde to the left. So if this is x of n, x0, 1, 2, 3, so x of n minus 2 modulo n is rotating the samples by 2 steps. So x0 will be rotated by 2 steps, it will appear over here. And all samples will be circularly shifted, so x of 6 will appear at n equal to 0. This is circular shifting by 2. Similarly, we have a property for circular shift in frequency domain. So if you know x of n with the n point DFT x of k, circularly shifting x of k by m will result in having a sequence in time domain x of n times wn to the power minus mn, where m is a shift happening in frequency domain. Again, it can be realized by circularly shifting the samples in a circle. You will be shifting counterclockwise if m is positive, you will be shifting clockwise if m is negative. In MATLAB, you can use the command shift to do the circular shift we have. You can use MATLAB to verify all the properties we have seen so far in this chapter. Next property is the duality property. It simply says that if we know x small of n has a DFT x capital of k, if we bring x capital of k, the sequence happening in frequency domain, we bring it into time domain. We make it x capital of n. Then the DFT will be the same sequence x small which was happening in time domain, but circularly folded and multiplied by n. In order to better understand this property, let's move to MATLAB one more time, and we have defined the sequence x1 of n, which is 1, 2, 3, 4. Computing the DFT x1k of this sequence x1 n, we will get 10 and minus 2 plus j, minus 2 and minus 2 minus j. The property simply says that if we have this x capital of k sequence considered to be a time domain sequence, if it's assumed to be capital X of n, so we're dealing with it as a time domain sequence, and we compute its DFT, so FFT of x1k, what should we expect to get? We should be expecting the same time domain signal, which was 1, 2, 3, 4, circularly folded and multiplied by 4, which is the length of the sequence. So I should be expecting something like this: 1, 2, 3, 4, circularly folded, so 1, 4, 3, 2, multiplied by 4, which is 4, 16, 12, 8. So the duality property simply says that if you have a sequence x of n and its transform x capital of k, if you deal with x of k as a time domain sequence, if you deal with it as x capital of n, in this case, performing DFT, you will get n capital, which is the length of the sequence, the length of the DFT operation, times x of minus k modulo n, which is a circularly folded version of x of n. The last property over here is the Parseval theorem. It simply says that if you have two sequences, x of n and y of n, and you know their transforms x of k and y of k, so summation of x of n times y conjugate of n, or in time domain from 0 to n minus 1, is equal to 1 over n summation of k from 0 up to n minus 1 of xk times y conjugate of k. Of course, if x of n is equal to y of n, we will be getting summation magnitude x of n squared, and here summation of magnitude x of k squared. The next property is the circular convolution. Remember that we have seen what's called the linear convolution before. Linear convolution is defined as summation from minus infinity to positive infinity h of m times x of n minus m, or summation x of m times h of n minus m. And using the DFT, we know that the linear convolution in time domain is equivalent to multiplication of the spectrum in frequency domain, or in z domain, y of z is equal to x of z times h of z. So now that we're dealing with DFT, given that we have two DFT sequences, x of n and h of n, each of length n capital, we can compute the so-called n-point circular convolution as follows. So the circular convolution is denoted in different ways. Some textbooks just use the notation of a linear convolution and put a circle around it. In the textbook we use n capital with a circle around it. So this n capital with a circle around it means n-point circular convolution. So computing the n-point circular convolution between x of n and h of n is defined as follows. Summation h of m x of n minus m Modulo-N from m equal to 0 up to n minus 1, or x of m times h of n minus m summation going from m equal to 0 up to n minus 1. If you compare this form with the linear convolution, you will find two differences. The first difference is that here the shifting and narrowing is done in a circular fashion. Instead of having x of n minus m, now it's n minus m Modulo-N. So we have circular shifting and circular folding. And the second difference is that in linear convolution we have summation going from minus infinity to positive infinity. Here the sum goes from 0 up to n minus 1, which is one cycle only. And the length of the output y of n over here is also n. So if x of n and h of n are n-point sequences, and we're doing n-point circular convolution, the output y of n, or the result of convolution y of n, is also n-point. And the circular convolution property in DFT goes as follows. The circular convolution performed in time domain is equivalent to multiplying h of k and x of k in k domain or frequency domain. So n-point circular convolution is multiplication of the corresponding DFT coefficients, h of k and x of k. So example, let's assume we have a sequence x of n is starting at x0, x1, x2, and x3, a 4-point sequence, and h of n is also a 4-point sequence. I need to compute the 4-point circular convolution. So the definition is summation from m equal to 0 up to 3 h of m times x of n minus m. So doing this, we will first draw two circles inside each other. The inner circle will include h of m, and the outer circle is x of n minus m. And first we will do n equal to 0. n equal to 0 will give us x of minus n, which is circularly folded x of n. So x0, x3, x2, x1. So the inner circle is h of n, or h of m, and the outer circle is x of minus m. And now they are multiplied together, which will give us x0 times h0 plus x3 times h1 plus x2 times h2 plus x1 times h3, something like this. At n equal to 1, we have h of m multiplied by x of 1 minus m. So it will be like this. We will be circularly shifting this x of minus m. So x of 0 starts here, x of 3, x of 2, x of 1, doing the multiplication and the summation. When n is equal to 2, we'll shift by 2 steps. n equal to 3, we will circularly shift by 3 steps. So we can do the circular convolution graphically like this. And these will be the 4 equations computing the circular convolution at n equal to 0, 1, 2, and 3. If we compute at n equal to 4, it will be equivalent to n equal to 0. Because if we try to shift this signal one more time, we'll get x0 back here, and x3 will go over here, which is equivalent to the situation at n equal to 0. And these 4 equations, as a matter of fact, can be put in a matrix form like this. So h0, h1, h2, h3 can be put in a column vector like this one. And here we can form a 4 by 4 matrix or n by n matrix. The first column of which is x0, x1, x2, x3. The next column is a circularly shifted copy of the first column, so x0, 1, 2, x3. The next column is a circularly shifted column, x0, 1, 2, 3. And the fourth one is also a shifted version, x0, 1, 2, 3. If you take a closer look, the first row is x of n circularly folded, so x of 0, x of 3, x of 2, x of 1. So you can very easily build this matrix, multiply it with this column vector, and you will get the result of circular convolution. And this approach is much more easier than doing the two circles inside each other and doing the rotations regularly. So here all you need to do is to write this vector, column vector, with one signal, and the matrix n by n with the other signal. The first column is the signal, and the other columns are circular shifting of this signal. Let's skip this part for now, so slides 47 and 48. Except for point 8 and point 9, you can actually compute this matrix using a command called typelets. I will leave it to you guys to verify it and to verify the property, which is circular convolution and multiplication in the frequency domain. The next property is called the windowing property. When two sequences are multiplied together in time domain, the result will be circular convolution in the k domain and dividing by n. And this is similar to the property before that. The property before that was circular convolution in time domain resulting in multiplication in frequency domain. Here it's the other way around. Multiplication in time domain will give circular convolution in k domain and dividing by n. Now, a very important consequence of what we have learned so far is computation of linear convolution using the DFT or using the FFT. Usually in DSP, the operations that we are interested in is not circular convolution. We are always interested in linear convolution. Why? Because LTI systems are governed by linear convolution. The output from an LTI system is equal to the linear convolution between the input and the impulse response. So we're always interested in computing the linear convolution. But what if we can compute the linear convolution using the discrete Fourier transform or the fast Fourier transform? The fast Fourier transform is an efficient way of computing the DFT. So if we can use DFT or FFT to compute linear convolution, we'll probably be doing it a bit faster and in a more efficient manner. So in this section we will learn how to compute the linear convolution using DFT. Why? Because computing linear convolution using DFT is computationally more efficient if we use the fast Fourier transform. Using the fast Fourier transform will be more efficient in the computational point of view. So this block diagram over here summarizes the process. There is a mathematical proof behind this flow chart or this block diagram, but let's just skip the mathematical derivation and do the final result. So if we have a sequence x of n whose length is L, that's defined from 0 up to L minus 1, and let's assume we have an h of n signal which is defined from 0 up to m minus 1, so its length is m, and we need to do linear convolution using the DFT or using FFT. First, we need to do zero padding such that the lengths of the sequences become n capital, which is equal to L plus m minus 1. L is the length of x, m is the length of h. So we need to do zero padding in order to have a length of n which is equal to L plus m minus 1. Once we do so, we compute the endpoint DFT, multiply them together, and then do the inverse DFT, and this will give us the linear convolution. In order to understand this, let's move to MATLAB and see how it goes. So over here we define the sequence x of n 1, 2, 3, 4 and h of n 3, 4, 5, and let's say we want to do linear convolution. There is a command called conv, so conv xn and hn will give us the linear convolution. Now let's say we want to do it using the FFT. So the length of the sequence x of n is 4 and the length of the sequence h of n is 3. So we need to do zero padding such that the length of the sequences becomes 4 plus 3 minus 1, L plus M minus 1. So 4 plus 3 minus 1 is 6. So we can do it in different ways. So I can define xn zero padded, which is equal to xn, and then I will add 2 zeros. This way it will have a length of 6. And I will define hn zero padded, which is hn, and I will be adding 3 zeros, which will be also of length 6. Now, if I do FFT of xn zero padded multiplied by FFT of hn zero padded, and then we do IFFT, now I'm simply applying the flow chart we have just seen. I did zero padding, FFT, FFT, IFFT. We'll be getting exactly the same results, 3, 10, 22, 34, 31, and 20. So this flow chart simply is saying that do zero padding such that the new length is L plus M minus 1. And then do FFT and then IFFT and you're done. We can do it differently. So I can use, okay, FFT of xn and specify the length to be 6. And here FFT of hn specifies the length. So instead of actually doing zero padding in MATLAB, you can do FFT and specify the length. And the FFT command will do the zero padding for you. So this command over here is simply saying that compute the 6-point FFT of xn. xn is only of length 4, so MATLAB will be adding 2 zeros and doing FFT. And this command over here will compute the 6-point FFT of hn. hn is only of length 3, so MATLAB will be adding 3 more zeros and do the Fourier transform. And again over here, if we try to do it, so xn and then 6 and hn and then 6, you'll get exactly the same result. And this supposedly is more computationally efficient than doing the linear convolution as usual. So in order to do the linear convolution using DFT, we need to zero pad such that the new length is L plus M minus 1, and then do endpoint DFT and then multiply and then do the inverse DFT. So please note that if n is larger than or equal to L plus M minus 1, then the circular convolution is identical to linear convolution, and hence you can perform linear convolution using FFT and IFFT. But if n is less than L plus M minus 1, then we will have a so-called time domain aliasing, and the circular convolution will not be identical to linear convolution. And of course in MATLAB you can do it like this, IFFT of FFT of xn and n capital times FFT of hn and n capital, and MATLAB here will do zero padding for you. The efficiency of this approach mainly depends on the length of the impulse response M, the hardware and software available, the memory available, and so on.